So hi all, welcome back to the lecture series on solving previous year questions of GATE ECE, and we were solving the questions related to digital electronics. So this is the first question, today's first question from GATE 2021. If 1235 in base x is equal to 3033 in base y, where x and y indicates the base of the corresponding numbers, then for what values of x and y these two values are equal? That's the question. Okay, so we'll just write first 1235 in base x. So we know if this is in base x, then the value will be equal to 1 into x power 3. So here this corresponds to x power 0, this corresponds to x power 1, this corresponds to x power 2, and this corresponds to x power 3, right? So you can write 1 into x power 3 plus 2 into x power 2 plus 3 into x plus 5. This is the actual value, right? So we'll do one thing, we'll write, so given the option x equal to 7, 8, 6 or 9, right? So if I substitute x equal to 7, what we need to do is, like, we need to substitute the values of x in this option so that we can directly get the value. Okay, so if I substitute the x equal to 7, the value will be equal to 467, and if x is equal to 8, the value will be equal to 669, and if x is equal to 6 as per option C, then the value will be equal to 311, and when x is equal to 9, the value will be equal to 923, right? So this is for the first given number. Okay, now I will take the second number, that is 3033 to the base y. Okay, so this also I can expand as this equal to 3 into y power 3 plus 0 into y power 2 plus 3 into y plus 3. Fine. Here also I will put the remaining y value of option A to D, that is y equal to 5, y equal to 6, y equal to 4 and y equal to 7, right? So if I substitute y equal to 5 as per option A, the value will be equal to 393. If I substitute y equal to 6, then the value will be equal to 669, and when y is equal to 4 as per option C, then the value will be equal to 207, and when y equal to 1053, then the value will be, sorry, when y equal to 7, then the value will be equal to 1053. So from here, if you see, when x equal to 8, then the value is 669 in LHS, and y equal to 6, then in RHS the value will be equal to 669. So both will be equal. So which means 1235 base 8 is equal to 3033 with base 6, right? So answer is B. Okay, so we'll see the next question. It is again from GATE 2021. The question is, the propagation delay of XOR gate, AND gate and the multiplexer in this circuit shown in figure are 4 nanosecond, 2 nanosecond and 1 nanosecond, so respectively. So XOR gate, so here XOR gate is there, it is of 4 nanosecond delay, AND gate is of 2 nanosecond, so this is 2 nanosecond, this AND gate is of 2 nanosecond, and this AND gate is of propagation delay 2 nanosecond, and mux is of 1 nanosecond delay. Okay, so that is a corresponding delay of each component here. The question is, if all the inputs P, Q, R, S and T are applied simultaneously and held constant, the maximum propagation delay of the circuit is. So we carefully check here. So P, Q, R, S, T, I can give any value. So if T is equal to 0, okay, if T is equal to 0, in mux this S0 will be 0, right? So what happens, the output of mux will be the input from this XOR, Okay, this will be the input here, and what will the output y? Y will be the corresponding to input at 0, this one. So here if I select 0, the actual path here will be, the actual path will be this one. This will be the path 1. So I will select this as path 1. Okay, path 1. So in path 1, what is the component, what are the total components from the input to y? That is from p to y, right? So it has 2 nanosecond delay here and 1 nanosecond delay. So I have 2 plus 1 nanosecond or 3 nanosecond delay. Okay, now if I select okay, so now say if t is 0, sorry, t is 1, okay, t value of t is 1. So what happens? The output of first mux will be the input from 1, right? So this is the path. Okay, and here if it is 1, what is the input from this NAND? That will be the output y. So the total path will be this one. So I will call it as, this is the path. I will call this at path 2. Okay, so if I take path 2, what is the total delay? Delay from AND gate 2 nanosecond, delay by mux, that is 1 nanosecond. Again I have a AND gate here 2 nanosecond and mux 1 nanosecond. I have 2 plus 1 plus 2 plus 1 nanosecond, or this is equal to 6 nanosecond, right? So among this, the delay of path 2 is greater than path 1, right? Which means that is the propagation delay, right? Maximum propagation delay will be the maximum value, that is 6 nanosecond. So answer is C. Fine. Yeah. Now coming to the third question. This is from gate 2021. The question is, the propagation delay of the XOR gate in the circuit in the figure is 3 nanoseconds. So this XOR gate has a propagation delay of 3 nanoseconds. The propagation delay of all the flip-flops are assumed to be 0. The clock frequency provided to the circuit is 500 megahertz. So here the clock frequency is of 500 megahertz. Okay, so what will be the clock time Tc? That will be equal to 1 by 500 mega, or that will be equal to 2 nanosecond. So 2 nanosecond is the time period of the clock. So starting from the initial value of flip-flop outputs Q2, Q1, Q0 equal to 1, 1, 1. So initially each value of Q2, Q1 and Q0 is set to be 1 with D2 equal to 1. The minimum number of triggering clock edges after which the flip-flop outputs Q2, Q1, Q0 becomes 1, 0, 0 in integer. So the question is like we have set it as 1, 1, 1. From that instant, how many clock cycle or how many rising edge of the clock is required so that the output becomes 1, 0, 0. Okay, so what we will do, we will just draw the clock cycle first. Okay, so these are the clock edges. Yeah, and okay, so at each clock edge the output Q2, Q1, Q0 will change. Okay, and we know the time period is 2 nanosecond. Okay, so but if some input changes at the input of XOR, the change will be seen at the output of the XOR after 3 nanoseconds. So we'll draw that also. So so this is 2 nanosecond, means any change happening at this end point will be seen at the output of XOR after 3 nanoseconds. So I'll draw, it will be something like this, right? oh, not here, sorry. So this is 2 means this will be 3 1, right? So if it is 50 percentage duty cycle means this will be 3 nanosecond from this edge. Okay, again from this edge where the flip-flop output changes, from there this will be the point at which the output of XOR will change. Again next to this one 3 nanosecond from this point. Okay, again from this node the next 3 nanosecond is this one. Again from this node this will be the output change at which output point at which, or the time point at which the XOR gate output will change, right? Yeah, now we'll start. So initially let given the output of XOR is 1, so we'll say this is output of XOR, so that is D2 is 1 here. Okay, D2 is 1, and let Q2, Q1 and Q0. Okay, it is 1 here. Okay, this is 1, this is 1, and this is 1. Okay, and from here it is clear that in each clock edge Q0 will become Q1 value, right? Q1 will become Q2 value, and Q2 is equal to D2. Okay, and what is D2? D2 is equal to Q0 XOR Q2. Fine. So if you see here, what is D2? D2 should be actually Q2 XOR Q0, right? Q2 XOR Q0 is 0, but that change happens from this point to next after 3 nanoseconds. So it will change to 0 at this point. Okay, at this point it will change to 0. Okay, after 3 nanosecond. Fine, but whether this change is reflected in the output of Q2, Q1, Q0? No, because at this clock edge the input to Q2 is still 1 itself. So the output Q2, Q1, Q0 will remain at 1 till the next clock cycle. Okay, so this is 1, 1 and 1. Okay, now here what happens at this clock edge? Okay, what happens to Q2? This 0 will be reflected at Q2, so here it will be 0 till next clock edge, while Q1 is still 1, right? Previous input of previous output of Q2, so it remains at 1. This also remains 1, so this is 0, this is 1 and this is 1. Fine, and now if you see at this point, okay, at this point the Q2 is 0 and Q1 is 1. Okay, Q1 is Q0 is 1. So 0 XOR 1 is actually 1. So but that will be that effect will be seen after 3 nanoseconds. So from here to 3 nanosecond it will be 0. Okay, and at this point it will change to 1. Okay, so nearly 3 nanosecond from this point. Right, now at this stage what happens? So here next will be, here this will be 0. Okay, Q2 will be 0 till next clock cycle, and Q1 will be 0 now, and Q2 will be same as 1. So here it is 1, here it is 0, here it is 0. Fine. Okay, now what happens in the next clock cycle? So here in the next clock cycle, here input D2 is actually 1. Okay, so Q2 becomes 1 here. Okay, and what happens to Q1? Q1 will be 0, right? Q1 will be 0, that is output of Q2, and what happens to Q0? That becomes 0, that is output Q1, right? So 1 0 0, and from here Q2 and Q1 is 1 and 0 respectively, so D2 will be 1, so that output from this point it will be reflected after 3 nanosecond, and again that will be 1 itself. Okay, now if you see here, the output Q2 has become 1, Q1 has become 0, and Q0 also 0. So that's what the question is. When does, after what number of clock cycle the output becomes 100? So which clock edge? So here clock edge 1, clock edge 2. So here I will write 1, 2, 3, 4, 5, right? So in the fifth clock edge the output changes to 100, or output reaches to 100. So the answer is 5. Okay, yeah, thank you.